Hi, everyone. My name is Christian Aganze. I'm currently at the University of California in San Diego. I usually work on brand doors, finding very decent brand doors, but this summer I adventured a little bit outside my comfort zone. And my project is on stream gaps in dark matter. So we're trying to find gaps in streams and use them to constrain dark matter properties. And this is done with my mentors, Dr. Sarah Pearson, G.K. Sandberg, and Catherine Johnston. So I have a really nice picture of Andromeda in the background. So the question we're trying to answer is, can we detect gaps in streams and use them to constrain dark matter with the Raman Space Telescope? And this is going to be in external galaxies. So we know streams exist in the Milky Way. We've seen globular cluster streams. If you remember Maddie's talk, she talked about Palomar 5. So this is one of the famous globular cluster streams. So the good thing about globular cluster streams is that they are actually tiny on the sky. So this one is 0.14 degrees width. And it's at 22 kiloparsec, and it's 30,000 solar mass, roughly. So we know they exist in the Milky Way, but we also know that they exist inside those things, those streams, there are substructure, which is what I'm highlighting there. So you can see a little bit of underdensity in one of the arms. And we think this could be because they're interacting with dark matter. And that's how you get those gaps. But Sarah also showed in her other papers that this can also be from the bar. So in external galaxies, streams do exist. And so this is an image from Martinez Delgado et al. 2021, where they showed some of the image from the DESI imaging stream imaging legacy survey. And you can see that there's some structures outside halos of external galaxies, and this is probably from the disruption of their satellites. So we want to find gaps in some of the streams in external galaxies, and we want to use that to constrain dark matter. And from numerical simulations, for example, Millennium simulations, which is what I'm showing here, we know that dark matter exists on different mass scales. So there is substructure that in all mass scales. And so this image here is showing like a 250 kiloparsec cutout of a Milky Way like halo. And you can see there is a lot of substructure around it. So we can basically use these streams to kind of constrain what's going on with the dark matter and back and forth. So I'm going to work through how I did that in the summer to try to create gaps in streams and see if we can detect them. So making gaps in streams. So first of all, to make the gaps in stream first, you have to make the stream. So I was using a very nice code by Adrian Price-Whelan. So this is the Gala mock stream generator. We create a mock stream. So as the cluster rotate around the galaxy, so this is the Milky Way potential. This is just a nice animation showing that the stars closer to the galactic center will be in this leading arm, and the ones that are a little bit further will be in this trailing arm colored by blue. And you can also look at that in the co-rotating frame with the stream. So as the stream goes through the galaxy, you release the stars and you create your trailing and your leading arms. So my goal was to actually try to create gaps in this. And so to do that, I have first to create a collision between a stream and the dark matter subhalo. So I'm going to walk a little bit through the cartoon. So they have to, so milk stream generator, how we use this, you have to put in a subhalo in the stream and generate that forward. The problem is that you may run into we want just to create one gap. So to do that, you only have to try to create one collision. So this is what this picture is showing. So we want to create a timescale so that we have the first collision. So here's the orbits of those two things. So that would be the stream going back and forth, and then the subhalo passing through it. And at some point, they collide, as you can see right there, where the movie ends. So we successfully can create a colliding orbit within 1 GeV. So then the next step is just to take that subhalo that goes through the stream, evolve a little bit with time t2. So that's what we did. So I can also visualize here. You have, so what I'm showing is that a stream that's already been created and the subhalo going through. So this is a very massive subhalo. It's 10 to the 10 solar mass. This is not what typical subhalos are. These typical subhalos are usually 10 to the 7, 10 to the 5. But you can see that it really messes up the stream. And so this is plotting X, Y, X, Z, and Y, Z coordinates, so you can see the entire interaction. So, okay, so we can create, we can send the subhalo to a stream and then integrate the stream forward after taking out the subhalo, so the subhalo is no longer interacting with the stream, and then let the gap evolve, which is what I'm doing here. I'm just plotting the same coordinate system, and the stream is evolving with time. So after that, you get a gap. So what you see here is the same, basically I'm plotting the same coordinates, so X, Y, X, Z, and Y, Z. And the blue dot here is showing the position of the progenitor of the stream. And you can see that there's a gap forming right there. So the next thing is to move this to M31 and see if we can actually observe these kind of streams. So I'm going to move away from this massive stream, and I'm going to create a Palomar-like 5 stream in M31. Put a gap in there and see if you can actually detect it. So we want to do this because Roman is going to be probably able to observe these kind of things. So let's get to the Roman telescope. So the next egress Roman telescope is going to be this large field of view telescope in the infrared and optical. And so here I'm plotting an image of Andromeda. And we're superimposing 2 pointings of the Roman versus 432 Hubble fields. So this is a small square here. You can see that only 2 pointings of Roman are equivalent to 432. This really large field of view is helpful because then we can actually see the entire stream in external galaxies. And one of those galaxies that we're interested in is M31. So we put this stream in M31. So I'm going to walk you through what this means. So this just means that we scale the width of the stream. This is a Palomar-like 5 stream, so it's roughly the same mass as Palomar, roughly the same number of stars. And we scale the width to match what it will be in Andromeda at around the 30 or 30 kiloparsec. So the number of stars here in this stream depends on like the isochron that from Palomar 5 like isochron. So this is something that Sarah did in her previous paper where they basically count how many number of stars do you expect to see in Palomar 5. And so in if you observe with Roman. So you can see that if you expose for 1 hour, you will see, can you see the gap? Where? Right there and right there. So there are 2 gaps. One of them is just because after you stop releasing stars, you can just evolve the stream, and where the position of progenitor, you'll find the gap there. And the other gap is from the dark matter subhalo going through. If you expose for 1,000 seconds, you probably cannot distinguish between, you can still see gaps. So that's good. But you can also add background stars in this. So these background stars are generated from other isochrons or sets of isochrons that mimic what you expect to see. So this is roughly based on the PANDAS data. And then what I'm superimposing here in yellow is the Roman field of view. And you can see that we can actually, that field of view fits where we see the gap. So it could have been that, the field of view is too small for the gap. So in principle, you're actually probably going to need different squares all around the stream, so you can actually see where you start getting a drop in density of stars. So if you zoom on that part of the Roman field of view, so this is just the same plot, you can see that you see the density contrast visually between the stream and the background stars, but you also see the density contrast when you start forming the gap. So where the gap is. And to even make it better, you can make a metallicity cut there. So if you make a metallicity cut, let's go back and forth. You can see that you probably see visually better the density contrast between the stream and the stars. So this metallicity cut here is based on what we expect the metallicity of Palomar 5 to be. Remember I said it was minus 1.3, so we expect maybe all the things to be around that metallicity. But then we can even do better by doing some kind of density estimator, counting how many stars we actually see along a direction. So I'm going to walk you through this. So this is the same image I was showing, and we have we're just counting how many stars in this direction, and then we using a large bin size. So that would be like a kernel density, a large bin size. And then we use another kernel density with a small bin size. If you divide those two kernel densities, you will get like an overdensity. So the large bin with kernel density, just like tracking the number of stars along the direction. And then the small bin width is just tracking like the variation in that density. So if you divide those two, then you just get a flat line, then you get maybe some over and under densities. So then you can use some kind of peak finder algorithm to find those peaks, and that's how you can detect gaps. A better approach will actually be to quantify the significance of this detection using some kind of Poisson statistics. And that's something I plan to do. So the question was, can we detect gaps in streams in Andromeda with Raman or W first? And the answer is yes, we can. So we can actually detect these gaps in streams. So in the future, it will be actually good to do a better, more controlled experiments. I ran a bunch of experiments. They were not all successful. But this one, we want to explore the different subhalo masses. We want to do like encounter speeds at so if the subhalo is coming at a higher speed or a smaller speed, and how does this affect our detectability of these gaps? And can we actually put these streams at different places in Andromeda or other galaxies and see if we can actually detect these gaps? And then we want to actually be able to distinguish between different dark matter models. And so the good thing about Roman is that we're going to be able to see the sample size is going to be really large. So right now we know streams in the Milky Way, but with Roman we're going to be able to see like a lot of galaxies. So that's going to really increase the sample size to maybe a few hundred galaxies, and you can just see streams in those instead of just being limited to the Milky Way. So there is a lot to do in the future, and there's a lot of future prospect in here. So I want to thank everyone. So first, my mentors, Sarah, Chiske, Catherine for guiding, and Adrian for guiding me through this, and Adrian for answering my questions and letting me make a bunch of gifts. And I learned a lot about streams this summer, and I learned about dynamics. And my fellow grad students for being kind and nice and helping me go through this summer. Thank you.
Awesome talk. Can you tell me more about the background star assumptions that you made, like how you modeled those? Does that make sense?
Yeah, so the background stars are actually from this data from a different paper. So I think these are from the parsec isochrones, and you just pick a batch of like a small square in Andromeda where you expect the stream to be, and you see what kind of stars you expect to be there. So that's where those background stars came from. Maybe Cheesecake can also talk a little bit about it because she's also the person that generated those stars.
Sure. Yeah. So we basically what Christian said, we fitted different isochrones to the PANAS data for Andromeda in small regions, and then extended those isochrones to or the luminosity functions corresponding to those isochrones to what Roman would be able to see, and redistributed those stars. So because we did different, fitted to different patches in Andromeda, we have the overall density distribution of the halo roughly correct.
Yeah.
But within the small patches, the stars are uniformly distributed because we don't know the small scale density structure.
Yeah.
But because they're small patches, we have the overall density gradient correct.
Yeah, so the density usually will fall off, but in those squares, it's okay to assume a uniform density.
Do you think we're in a regime where we can like genuinely trust only photometry? Like metallicity seems like it would really, help you like say like this is certainly a stream, but do you think that we can be at a point where it's like we see it in photometry and we can be positive about that, or like how much do you need external information to verify what you will find?
Let me see if I understand your question correctly. The purpose of this was not to detect the stream, because Sarah has shown that you can actually take the stream. It's actually see if you can see the gap in the stream. So that metallicity cut there, I think it does do like show a little bit of, here you can see that, but this is one experiment. You can see that it does actually improve visually if you can see the gap. If there are other ways you could actually, besides like putting a significance on the detection, I will have to think about that.
So for your dark matter subhalo, was that like a point source or was that an extended distribution?
Yeah, that was an extended distribution. You assume some kind of a Plummer sphere or some kind of a Henquist profile, or I tried all kind of profiles. Yeah.
Okay, and did you look at whether that changes the velocities along the stream in any way? Maybe like near the gap or even in other parts of the stream?
Yeah, that's a good question. What changes a lot? I haven't seen like how different density profiles changes that, but if you change the scale radius of the subhalo, you do see a difference there. I think I even had a GIF. Maybe I can show that. Maybe not. But yeah, so if you mess with the scale radius, so there's some degeneracies. So I think that's also in one of Adrian's talk. Sorry. I want to just show what the degeneracies are here. So there's some degeneracies between like, not just like the shape, not just changing the dark matter profile, but also like changing the scale radius. So in this case, you see like the rough morphology of the gap as you change different things. So as you increase the mass, the gap becomes more apparent. If you decrease the impact velocity, because you have like, I think, more interaction time with the stream, you get a larger gap. If you reduce the scale radius to a smaller scale radius, you get a larger gap. Also, the impact parameter also can also affect that. So this is like approximate analytic formula from some work that Kathleen did with Dion, and you can see that there's some degeneracy between things. So it's kind of hard. It's going to be hard to tell. Like, I see a gap, and we can actually learn about dark matter. So we still have maybe some steps to get there.
Hi, this is great stuff. I had a question I didn't understand. So you made a cut in metallicity. Is that a cut in metallicity that you were able to make with just the photometry, or would that be assuming that you had spectroscopy for everything that you could get a metallicity?
Forget it. I think these were photometric metallicities. That's right. These are photometric metallicities. So you don't need spectroscopy to do this.
It was a great talk, firstly. I was wondering, what do you think are the prospects for discriminating between the effects of subhalos and forming these gaps versus, say, the effects due to the bar?
That's a good question. So the effect of having a subhalo versus how can you distinguish that from the bar? If the stream is very far away from the galaxy, that it's probably not going to be affected by the bar. Maybe you can trust that it's probably the same halo, but it's probably more complicated than that. Yeah, so that would be my to-go-to answer for that.